Welcome students. This session we will start fractals, fundamental of fractals. The objects which are having smooth surfaces and regular shapes are generally described by using equations. But natural objects such as mountain, trees, ocean, waves and clouds have irregular shapes. It will be very difficult to draw these shapes by using normal equations. It cannot be represented with Euclidean geometry methods. There are many methods of modeling these natural objects, but one of the most interesting from a mathematical perspective is that of fractals. So we can describe natural objects by using fractals, where procedures rather than equations are used to model the objects. Procedurally defined objects have characteristics quite different from objects described with equations. One of the basic properties that characterize fractals is self-similarity. What are fractals? We can define a fractal as an object or quantity that displays self-similarity in a somewhat technical sense on all scales. Fractals need not exhibit exactly the same structure at all scales, but the same type of structure must appear on all scales. The self-similarity property of an object can take different forms depending on the choice of fractal representation. Self-similarity means if we zoom into a piece of fractal, we will keep seeing the same structures repeated over and over. As one zooms in or out, the geometry or image has a similar, sometimes exact similar appearance. There are certain types of self-similarity, that is exact self-similarity, approximate self-similarity, and statistical self-similarity. This one is the example of self-similarity which may be exact. Normally only occurs in mathematical defined fractals. Example is of Koch curve. We will see this Koch curve and Koch snowflake in detail further. From a certain distance, we will see a coastline as a simple, quite smooth line, but as we go near to that line, it will appear more rough. If we take closer view, we will see the whole line as jaggy and rough. There is no limit how many times we can zoom. The generation of fractals is with the basic principle that can be shown here as P0, which is a function of x0 and y0 for initial point. The same function f of P0 will repeated with different values, that for P2 it is equal to f of P1, that is equal to f of P0. P2 is equal to f of P2, that is equal to f of P1, and that is equal to function of P0. Imagine that one object is made up of clay. If we break that object in terms of line or line segments, then we will give the dimension d is equal to 1. If the object is broken into a plane, then we will give the dimension d as equal to 2, means 2 dimension. And if the object If we break that object in terms of line or line segments, then we will give the dimension d is equal to 1. If the object is broken into a plane, then we will give the dimension as d is equal to 2, that is 2 dimension. And if the object is broken into 3D objects like cube, sphere, etc., then we will give the dimension as d is equal to 3. Here, the variable d is called as topological dimension. Now imagine that we have a thread or line of say 5 cm. If we cut this in 5 equal parts, that is, each subthread's length will be 1 cm, which is shown here in this figure. Suppose this is a line of 5 cm. Now, if we want to build original object from the scaled one, now imagine that we have a thread of say 5 cm. If we cut this into 5 equal parts, that is each subthread's length will be 1 cm. It means we have scaled the thread that is lying by 1 by 5. Now if we want to build original object from the scaled one, then how many scaled objects will be required to form the original object? Obviously, the 5. This figure was explained here that R is equal to 1 by n, whereas n is equal to 5 in this case. Now consider a square. A two-dimensional square. And if we want to scale it by 1 by 2, then how many small squares will get generated? If we want to scale it 1 by 3, how many squares will get generated? 9. Now, if we want to build the original square again, then we need n number of scale objects, that is 9. So here is n is equal to 3. Similarly, if we have a 3D object like cube, and if we scale it to 3, then we need 27 cubes. If we observe this, we will come to know that there is some relation, that is the exponent goes on increasing. R is equal to 1 upon n raised to 1 by d. That is d is equal to log of n by log of 1 by r. It means if we scale an object of scaled objects to reconstruct the full size of original object, then the dimension of the object is given by d is equal to log of n by log of 1 by r, where this d we called it as a fractal dimension. The number of segments, that is n, the segment length similarity ratio, that is r, and the fractal dimension d is given by log of n by log of 1 by r. For n is equal to 4, r will be 1 by L, that is 0.5 and d is equal to 2. Self-similar dimension: an object has dimension d if, when it is subdivided into n equal parts, each part must be made smaller on each side by r is equal to 1 by l or 1 by n raised to 1 by d. The fractal dimension will be given by formula d is equal to log of n divided by log of 1 by r. We will see this fractal dimension Koch curve after explaining Koch curve. Very complex curves can be made by repeatedly refining a simple curve. The simplest example is Koch curve, discovered in 1904 by Helge von Koch and Swedish mathematician, which is exactly self-similar fractal Koch curve. Fascinating feature is that an infinitely long line within a region of finite area. The fascinating feature of this Koch curve is that we get an infinitely long line within a region of finite area. To draw a Koch curve, we have to start with a line segment. Then we are dividing that line segment into three equal parts. After that, we are replacing the central third part by two adjacent sides of an equilateral triangle, which is shown here. This gives us a curve whose end coordinates are same as that of original segment, but is still of four equal length segments, each 1 by 3 the original length. So the new length of the curve will be 4 by 3 of the original length. We have to repeat this process for each of the four segments. The next figure beside to this shows that appearance of Koch curve after second approximations. After second approximation, the length of the curve becomes 16 by 9 times the original length. Now we can easily say that the length of Koch curve is infinite, because again this each line can be converted into the second approximation. Into the first approximation. It doesn't deviate much from its original shape. If we reduce the scale of the curve by 3, we find the curves look just like the original one, but we must gather 4 such curves to make the original. Therefore, Koch curve topological dimension is 1 and fractal dimension is 1.26. From one generation to the next, n is equal to 4 segments are created from each parent segment, but their lengths are r is equal to 1 by 3. Due to this, we can calculate t is equal to 1.26. From this discussion, we can say that curves whose fractal dimension is greater than its topological dimension, then they are called as fractals. This is example by taking Koch curve with 3 lines connected to each other. which is exactly an equilateral triangle. And generating the approximations again and again, we get Koch snowflake. Next point we are having is fractal lines. We know that a curve is composed of n self-similar pieces and each piece is properly scaled. Now, if we want to draw a coastline by using fractal line, ideally it is infinite. But as we are using computer to generate that curve, we must terminate our program somewhere. So the terminating condition could be the length of the curve. That is, when the length of the curve becomes less than the size of pixel, we should terminate our program. To generate the fractal line, we have to perform following steps. If the user provides two endpoints of line as shown in figure, first point x1 y1 z1 and second point x2 y2 z2, then we have to find the halfway point for the fractal line. This halfway point can be calculated from the midpoint of the line as xm equal to x1 plus x2 divided by 2, ym is equal to y1 plus y2 divided by 2, and zm is equal to z1 plus z2 divided by 2. But in order to achieve the halfway point, we have to add some offset to each coordinate midpoint. That will give us this halfway point. That xm is equal to xm plus dx, where xm is equal to x1 plus x2 divided by 2. Similarly, ym is equal to ym plus dy, and zm is equal to zm plus dz. That will gives us this halfway point. Here, this offset dx, dy and dz must be random values. Basically, the necessity of random value is that in nature, the objects are not smooth. In case of coastline, we will never see a natural coastline as a straight line. At some point, it may be inside, and at other position, it may be opposite side, as shown here. So to get this random effect, we are using offset, which is random value, which is going to add in this xm, ym and zm by value dx, dy and dz. We can calculate this random offset by a formula dx is equal to L into W into cos, dy is equal to L into W into cos, dz is equal to L into W into cos, where L is the length of the segment and W is the weight factor for roughness of the curve, that is fractal dimension, whereas cos is equal to some random average value between -1 to 1. This halfway point divides the original line into two parts. Again repeat the same procedure for each part separately. To draw a fractal line, the algorithm will contain a recursive procedure and the parameters for that procedure will be starting point, ending point, number of iterations and offset. Shows the generation of coastline by using fractal lines. Next, we are having fractal surface. We can draw coastline or lighting bolt by fractal lines. But if we want to draw a 3D object like say mountain, then we have to use fractal surfaces. The concept of fractal lines can be extended to generate fractal surfaces. There are many ways by which we can do this. Here are we will see some method which is based on triangle. We know that triangle has three vertex points. We can generate a fractal surface for the area between these three vertices as shown in this figure. The fractal surface can be generated by performing few steps. Like first, we will use fractal line algorithm to each edge of this triangle, compute its halfway point by the same logic as that of fractal lines which was seen earlier. Connect these halfway points by line segment. By doing this, we are now having four small triangles. Now we can call this procedure recursively to each of a small triangle until the triangles becomes too small as shown here in this figure. In this animation, we called different type of fractal, that is one triangle converted into another triangle by its center and so on repeatedly again and again. This is also one of the example of fractal surface. This is all about curves and fractals. We will stop here today. Thank you.